Hello, and welcome to another lecture in the course. Today we're going to look at why holomorphic functions are analytic. So if we have a holomorphic function, so a function that is complex differentiable at every point, then it has a power series at every point. So this is subsection 3.3.1 in the book. So this is the consequence of Cauchy's formula that we proved last time. So we already proved the other direction. We proved that if we have an analytic function, that means that if we have a function which has a power series at every point, that is, it's equal, in a neighborhood at every point, it's equal to a convergent power series, then it's holomorphic, because we proved that we can take the complex derivative of any power series, and the complex derivative is a power series that you get just by differentiating term by term. Right, so let's prove the converse. Let's prove that if we start with something that's complex differentiable, that it actually happens to be analytic, that it has a power series. So this is what we're going to prove. So you start with any open set U, a holomorphic function in U, so a function with a complex derivative at every point. We start with some arbitrary point P, and a disk, any disk, as long as it's contained in U. So any disk centered at P contained in U. All right. So then there is a power series such that the function is equal to the power series for all Z in the disk. Right. So on this disk that we started with, which was really just an arbitrary disk in U centered at P, on that disk, there is a power series which centered at P, which equals F. Moreover, we actually get a nice formula for these coefficients, right? I mean, the whole thing is about the existence of these coefficients. We actually get a formula for these coefficients, and it sort of looks like the Cauchy's formula. So with these funny powers over here, and the gamma, the cycle over which we integrate is any circle of radius little r, which is anything between 0 and capital R. So basically any smaller disk inside our capital R disk, right? And it's supposed to be oriented counterclockwise, so going in that direction. All right. So fix this little r, right? Any little r, just as long as it's smaller than capital R. One thing that it means is that the whole closure of the little r disk is contained in U. I mean, it's contained in the big R disk, right? So it's contained in U, meaning the circle is contained in U. That allows us to apply Cauchy. So let's fix a Z inside this little disk, right? And let's look at zeta that are on this boundary of this disk. So on the circle of radius R. And let's look at this expression over here, and we're going to see why that expression is important in a moment. So Z minus P over zeta minus P, and let's look at the modulus of that. Now, zeta is on the circle, and P is the center, so zeta minus P in modulus is exactly R, right? So we get that the modulus is this guy, and the top, Z minus P, modulus of that, well, Z is in the little r disk, so that's less than R, so the whole thing is less than 1. So that means that we can apply the geometric series. We can plug in this expression into the geometric series, and we get convergence. So, and what does it converge to? Well, it's 1 over 1 minus that expression, right? Which, if you do a little bit of algebra, is this guy over here, zeta minus P divided by zeta minus Z. All right. So let's apply Cauchy's theorem, right? So Cauchy's theorem says that z, because that was something in the disk, is equal to Cauchy's integral formula. I mean, is equal to this formula over here, right? We had this is the Cauchy integral formula in a disk, right? All right. So now, what I'm gonna want to do is I want to sort of separate the the z from the f, right? So maybe I want to separate the 1 over zeta minus z, pull it aside. Now, I want to use this formula over here, right? So here I have zeta minus z, but I also have zeta minus p on top, so I have to sort of pay for that, right? So I stick it in like this, right? So, I just multiplied and divided by zeta minus p, right? But now I have this expression over here that I know is equal to this series, right? And this series, by the way, that's the other thing. It has the z minus p to the n. It has precisely the thing that I want from my power series. All right, so I replace this guy with the series, right? Okay, so now what I want to do is I have two limits over here. There's the limit coming from the series, and there's the limit coming from the integral, and I want to swap them. So let's first not worry about why we can swap them. We can. Let's not worry too much about why. Let's just suppose that that we can, right? If we swap this, if we move this, I mean, I could clearly, put this guy inside here, but then the main thing is then pulling this guy out, right? What we would get, and we do a little bit of algebra, is this expression over here, right? And what we have is that this z minus p to the n, right? That's this guy over here. That's nice. That's the thing getting us the power series, right? Those are the terms of the power series, and then whatever remains, and this thing is the thing that doesn't depend on z, right? So this thing is that's our Cn, right? And you can actually notice that's exactly the formula for our Cn. The little disk, the circle of radius r, that's the gamma, right? So okay, so that's precisely what we wanted, right? Now, of course, the point is, can we, is this an equality? Can we do this swapping of limits, right? Now, we can swap limits with integrals. For example, I mean, there's a whole bunch of these terms, but for example, when you have uniform convergence, and we have uniform convergence here, we'll justify that in just a moment. So uniform in the zeta, right, where zeta goes over the disk. Really, it's uniform in the, it's like if I replace zeta, if I whatever parameterizing variable I use, right? So it's an integral from 0 to 2 pi, and then I'm gonna have e to the I t somewhere, right? All right, so let's see. So why is it uniform in the zeta? Right. So it's really this guy that needs to be, this convergence of this series that needs to be uniform, right? Because if you look at over here, right, I have to push this thing inside, and then that's what I'm swapping, right? So let's look at that. And we're actually going to look at the absolute convergence. So first, z is just some fixed number, right? I mean, as far as the convergence and as far as the integral, z is not moving. Z is a fixed number, right? Now let's suppose n is the supremum of this guy over here, and that is some fixed number, because f is well, at least continuous, right? We have we have a compact set, right? The circle. So this guy is a continuous function on a compact set. It achieves a maximum, right? So zeta minus p never, that never goes to 0, right? So that's always r. So as long as we are on the circle, right? That's where we're looking at this. So that means that there is some m that bounds this guy over here. All right. So that means that if I take the absolute value of the terms of this series, right, the modulus of that, I can bound it from above by this, right? And now I notice that this guy over here, well, that's strictly less than 1, and it doesn't depend on zeta, right? So first, this converges because it's really just a geometric series, right? I have something less than 1 to the n, right? The m doesn't really come into it, right? And so I have a geometric series, and the rate of convergence just depends on how large this number is, and that doesn't depend on zeta, right? So this is uniform, right? So what we really have is that this guy converges uniformly in zeta. That means that this guy converges uniformly absolutely, and that means it converges uniformly, right? So that's what we needed, right? We need uniform convergence to pass the, to exchange the limits, right? So we found a power series convergence to f of z for all z in the disk, right? So now we can, this work for any z in the disk, right? And now by uniqueness of the power series, if we look back at the formula, if I look at the formula, this guy over here, right? By uniqueness of the power series, because now we know that it's equal to in the little disk, in the little r disk, right? It's equal to this power series. Well, power series are unique, therefore the CNs are unique, right? Let's go back to this, right? So that means that, well, if I choose different little r, I mean, still I have another power series in some maybe smaller disk, right? That equals the same function, right? So therefore the CNs have to be independent of r, right? I mean, a priori they do depend on r, right? Because for different r, it's the formula looks different, right? It's integrating over a different circle, but I have to get power series, and they all in some neighborhood of p, they all have to equal f, right? So therefore, all the CNs are same regardless of what little r is, right? And well, since we get the same series for every r, every little r, we actually get convergence in the big R disk, because we could just pick an arbitrarily large little r. It still has to be smaller than big R, but if I have a z in the big R disk, I just choose little r that's a little bit bigger than bigger than that, and then so that the z is in the little r disk, right? And then I applied what I just proved, right? And I know that the series is still the same. All right, so that's the that's the theorem. Now the key in this proof is writing the Koji kernel, right? And by kernel here we mean I think I always get this question, whenever I say kernel here, everybody says, well, it's kernel of some, matrix or something. No, I mean, in analysis, a lot of times what people mean when they say kernel is a function against which you integrate. So you integrate one function against another function, right? And that another function is a kernel, and that's supposed to depend on another variable, right? So I'm getting another function. So in this case, the other variable is z, right? So I'm integrating f of zeta against 1 over zeta minus z, right? So I'm adding in one more variable, integrating against that. That's the kernel, right? So the Cauchy kernel, the key thing is to rewrite it as this, which then gives us then we can use the geometric series. So we really only know how to sum the geometric series, and we're using that, right? And I think I've said that before. Basically, the geometric series is the only power series which we really know how to sum. So that's the key point in here, right? Is to use the geometric series, and then it's swapping of integral and the series limit. Now, it's a fairly common technique that's being demonstrated here. The Cauchy kernel is analytic. Integrating against it, in this case, gets us an analytic function, right? And well, you have to always do this in the right way, but that's generally the idea, is that if you integrate against any function against some kernel, then what you get is that the function that you get out of that, which in this case is equal back to the function that we started with, although that's specific to this case. But the integral, the thing that we're getting, is a function that gains properties of the kernel, right? So in this case, it gains analyticity, right? Now, the fact that it equals the function that we started with means that the original function is analytic, right? So this is a fairly common technique, that you integrate against the kernel, and then it's this new function has something to do with the function that you started with. In this case, it's equal, but in general, it's going to have something to do with it. Maybe not being equal, but it's going to be a solution to some differential equation or whatnot. But it gains the properties of the kernel. So if you understand the kernel, you understand this integral, right? Now, besides the fact that it's analytic, we proved a rather strong thing that might be lost in how we phrased it. If we stick in any disk of radius capital R that fits in U, we got a power series that converged in that disk. That means that we also know something about radius of convergence of the power series for F. And it's actually equal to, or at least equal to, maybe it's bigger. Maybe U was not the ideal domain for this function, but if we know that F is holomorphic in U, then if we stick in the biggest disk around P that we can fit in U, the radius of convergence is at least that. So it only depends on where F is holomorphic, which is actually quite strong. I don't have to know anything else about F. I just need to know where it's defined. Now, out of this, one thing that we know is that if we have a power series, the radius of convergence, the way that you compute it, the way that you compute the coefficients are by taking derivatives, right? Or you can do it by taking derivatives of the function given by the power series. So it's the derivatives of the function at p, right, that are the coefficients, and the radius of convergence is some sort of a bound on how how these coefficients behave as n goes to infinity, right? And so we get some sort of bound on the derivatives in terms of the radius of convergence, right? The bigger the radius of convergence is, the smaller these guys have to be, or maybe not no particular one has to be smaller, but for example, if R is very big, then these guys have to go to 0 sufficiently fast, right? So we know something about the size of the derivatives of the function at p just by knowing how far away from p it is still holomorphic. And that should be a little amazing, right? Or at least I find it amazing, right? Because that doesn't seem like that should be true. And it's not true if we look at real analytic functions. That means functions that are given by power series, real power series. So everything is just real, right? So for example, 1 over 1 plus x squared, right? That has a power series. So there's you can find the Taylor series everywhere, and its Taylor series is equal to this function, right? But the radius of convergence, we can't figure it out just by looking at where this function is defined if we're only looking at real x, right? 1 over 1 plus x squared is defined for all x. It's really nice real analytic function on the entire real line. But the radius of convergence at 0, for example, is 1, right? So I can't figure out the radius of convergence by just looking at where it is defined. Now, in this case, one thing that you could notice is that, well, I could just plug in complex numbers for x, right? Could just, replace the x by a z, right? And if you plug in complex numbers, right, you get a nice holomorphic function. Well, not quite everywhere. It's not holomorphic at I and minus I, right? And well, if it's not holomorphic at I and minus I, then if I look at the origin and I try to stick in the largest disk around the origin, that still fits in the domain of 1 over 1 plus z squared, then, the radius 1 is the best I can fit in. So, all right. So let's restate the main conclusion of this. So we proved more, but let's just restate sort of the main conclusion and stick in the thing that we proved before. And so what we proved is that a function is holomorphic if and only if it is analytic, right? So holomorphic is the same thing as analytic, right? Now, what does that mean? That everything we proved for analytic functions is true for holomorphic functions. So there are certain things which are easy to prove for analytic functions, but are hard to prove, maybe, or harder without knowing this result. Will be harder for holomorphic functions, and vice versa. There's things that are easy to prove for holomorphic functions, hard to prove for analytic functions. For example, it is very easy to show just by chain rule that holomorphic functions, that if we compose two holomorphic functions, that the composition is holomorphic. If you try to do this, and it's possible, but it is much harder to do it for analytic functions just by, well, so I have two power series and I just plug them into each other and the result is a mess, right? Why is that a power series, right? Well, but I don't have to do it, right? I just know that if I want to know that composition of power series is a power series, well, I just know, well, the power series gives me a holomorphic function. Holomorphic functions I can compose and get a holomorphic function, and that holomorphic function in composition, well, that has a power series because it is analytic, right? So that's a much simpler proof than trying to plug the two power series in and trying to figure out if the resulting thing is a power series and if it converges and where it converges, right? So it's much harder to do by directly manipulating the power series. All right. Now, another thing that we've just proved that maybe is not quite immediate, and which was a little bit of a technicality. So before, when we defined analytic functions, we said an analytic function is something that in a neighborhood of every point, it has a convergence power series that converges to the function, right? But one thing that we didn't prove then is that a power series just done at a single point, right? So you have a convergent power series, converges in a disk. All that we proved before was that is holomorphic, right? We could differentiate it, and the derivative was a power series. But we didn't really know that function has a power series at other points, right? And that's possible to prove by directly manipulating the power series again. But again, we have an easier way of doing it. Once we know it's holomorphic, it is analytic, right? So we finally could have proved that fact in an easier way, right? So all right. So next time we're gonna look more at the derivatives. Actually, show that the derivative of a holomorphic function is holomorphic, and then you can probably guess why at this point, right? If you think about it for a little bit, and we're gonna find a nice formula for the derivatives that we've sort of already seen, and we'll look at Morera's theorem, which is sort of the other direction, the converse to Koji. So if something satisfies Koji in the right way, really Koji goes on. We're gonna just do it for triangles. So if something satisfies Koji for triangles, it is actually holomorphic, which makes it easier to sometimes decide that a function is holomorphic because it's easier to integrate. If you have just a continuous function, you can always integrate it. Than it is to differentiate. Differentiation is harder. All right, so we'll do that next time. So see you then.